Welcome everyone to join today's webinar. So today's webinar, we will focus on this Straylight analysis with Ansys optics. And today's design will be like design and validate the Straylight camera optics using the Ansys Speos and Ansys Zemax OpticStudio. So I'm Law, the application engineer from Cybernet System Malaysia. Okay. So what is the Straylight? So first we will start with to understand the Straylight. So Straylight normally we refer to the unintended source of light to reach the imaging sensor in the optical system, which this will impact the irradiance or the intensity distribution received on the sensor. So as this one, it is the negative impact on the optical performance on the system, and also it affects the image quality. So as you can see, the photo on as this show, so you can see the Straylight inside the smartphone camera. So you will see some circular ring on the image, and also in this head-up display inside the simulation, you also can see some unintended intensity light on the screen, which can blur the focus point. And this one is the camera, smartphone camera also, the Straylight, because the sunlight too strong, so the internal reflection, you can get also the ring and also the flower. So here we will describe how the Straylight, the illustration, the source, and also the form. Okay, so we need a object. We also have an image, and this is camera. So ideal path is the object pass through the lenses, and then all the light ray will ideally flash on this image sensor. But somehow, because we have some spherical lenses in between, so in the real situation, the light ray doesn't like the ideal ray that can enter the lens array and finally drop on this image sensor. So it will be having some internal reflection. So as this pink color light ray, okay. So this light ray, sometimes they will create like the lens flare, as you can see the image here, or the light ray they strike on this mechanical part. So there will like internal reflect between the mechanical part, and finally they will go into the imaging sensor. So this one you will get something like scattering. Okay, so and some of the light ray they will go into your this mechanical without going through your this lens array. So finally we will get something like the light leaking, so which is all the unintended light path to the imaging sensor. Okay, so as we know, all the camera system or other system, the Straylight is everywhere. So as you can see inside the HUD, the automotive and the ADAS system, and also inside the aerospace and defense, the AR HUD and the HMI display, and also the consumer electronic like camera and the AR VR scope, and also the space exploration inside the telescope. Okay, so this is the challenge and the Ansys solution. So when we deal with this high performance criteria, the high precision modeling and optimization criteria is very important. So the complex nature of the system require all the parameter and geometric. So for this kind of complex criteria, and it's time-consuming process to evaluate the Straylight. So it needs the collaboration of multiple departments and also participation of multiple disciplines. So for this kind of simulation, we get a lot of challenging. So in Ansys solution, we will give the simulation is the key to budget-friendly success. Okay, so we will like using the free space element design and optimization and the system modeling. And for this, the cross-platform. So actually, Ansys support this optical automation and also the PyAnsys toolset. So that means the automation of the process can be like data transfer within all the Ansys software. And next is the smart design optimization approach. And finally, it can reduce the engineering time and price to the automation. Okay, so before we start the workflow, maybe we can like simply briefly introduce the Ansys Optics product, the portfolio. So as you can see from the left to the right, left will be the numerical, and middle is the Zemax OpticStudio, and finally is the Speos. So we have the definition for the level of the design. So for this numerical, most of the design will be in the wave. So you can see the design will be in chip level. So the example of the application is the photonic component modeling, some such as this waveguide sensor and micro lenses. All the design will be in nanoscale. And in the Zemax OpticStudio, we will design on this optical component modeling. So most of the thing you will see is the lens stack. So we can do the optimization, the tolerancing, and also the stock analysis. Then all the design will be in macro size. And last one will be the system using Ansys Speos. So all the simulation in this photonic and also the optical component, we can group into this system and using our human vision precision to do the simulation to see the real thing. And also we can include the 3D environment integration and also the lighting. So to do the system level validation. So for today's workflow, we will only using this Ansys Optics ecosystem, which is the Zemax OpticStudio and also the Speos. One is the optical lens design, and another will be the system level validation, including the optomechanical analysis. And last one will be the scattering surface. So it's the surface to anti-reflection for this Straylight analysis. Okay. So today's workflow is an automation using the Python scripting. So this example, first part will be the Zemax, and second part will be the Speos. So the workflow block summary will be in this way. So initially, we're using the OpticStudio to analyze the lens performance. So after that, we were doing this ghost optimization, and we export this ODS. So after that, this thing will send to Speos to do the Straylight analysis. And inside the loop, we will looping the simulation to do the worst offender detection. So this detection will keep replacing the coating surface and also calculate and evaluation the SNR, the signal noise ratio. So this is the iteration loop until the SNR become better. Okay. So this is the initial workflow. So inside the Python automation, we have this kind of file structure, the directory. So the workflow can be run in this main workflow. So the main workflow will call up this coating cycle Zemax and coating cycle Speos. So this one is the main script for this main workflow to call up. But when we running, we using this main workflow. Okay, so all the button here will be the simulation file for Zemax and Speos, and also the library file to do the calculation and evaluation. So the user define is the target SNR and also the error budget for the optimization part. And the initial step will be connect to this ZOS API and remove existing coating and start clean optimization environment. Okay, so this automation will be like automatic, run repeatedly manual setup. And this is the initial step. So initially we doing all the design for the lenses in sequential mode. So after we confirm all the requirement met in this sequential mode, so we can first convert to the non-sequential ray trace. So as you can see, this photo is the non-sequential mode. So when we convert to non-sequential mode, we need to include this use polarization and also split the NSC ray, and we need to save the array for this ZLD file for the further analysis. So this is the output file. We're going to use the signal power, noise power, and also the ZLD ray database. Okay, so inside Zemax, actually we having some tools we can analyze the path, but this one only restricted inside the lens array without the mechanical part. Okay, so inside the Zemax, we have this NSC 3D layout. So you can see when after you get the ray database, you can apply the filter to see the ghosts until they hit the final element, the 25 is the last layer of the lens surface. So after that, you can filter out the ray source, and also you need to check the checkbox like use polarization, split the NSC ray, and the scattering NSC ray to see the ray path. Okay, so the next is the tools using the path analysis. So this is the old version we using, and this feature we still have. So these tools will generate the path. For example, path 1, what is the flux out and the percentage, and the sequence of the ray they pass through the lenses until the last layer. So in the new feature, we also include this sequence selector. So for this sequence selector, you can auto classify all the array into the direct stray, the ghost, and also the direct lights, like ray to the imaging sensor. So when you click on each row on this one, you will see the light path, how the light go to your lenses until the image sensor. Okay. So this one will use to identify the worst offender surface. So next one is the optical XNR improvement. So for this workflow, we having a definition signal to noise ratio. So this one, the higher the SNR, we can get the cleaner the image, and also lower the optical noise, improve the contrast. So the workflow here will be using the iterative until the target SNR is achieved. So this one will be done in this Ansys Speos to do this one. Okay, so next one important things is export to the ODX. So what is this ODX? ODX actually is the optical design exchange. So this is the feature to do the operate between Ansys OpticStudio and also the Speos. So the Ansys OpticStudio will output the lenses and also the light ray into the ODS file. So when we import this ODS file into Speos, you will get some solid, which is referred to the lenses, and also the ray path direction if we export on this one, and also including the optical properties and also the sensor. So after that, inside this Speos, we can import also our mechanical part. So the entire system will be the auto mechanical design in Speos. So we can do the Straylight analysis for the complete system in virtual scene. So inside this auto mechanical part, the validation. So the Straylight optical Straylight alone is not enough. So this one is inside the inside the Zemax, what we do is just the Straylight with the optical lenses only. So now we import into Speos. We have this housing reflection, the bevel scattering, and also the mechanical interaction. So inside Speos, the feature will be the GPU acceleration and the full system Straylight analysis and the phase filtering. So all these features will improve the Straylight analysis and also speed up the simulation. So as you can see, here is the part for the automechanical, and you can see also the automechanical part and also the buffer. And also we will every time iteration we'll try to apply the absorbing coating on the lens surface. So here we can like, if you have existing material, you can direct import into Speos. If you don't have it, you have a data, you can using the editor inside Speos to create this coating file. Okay. So next is the mechanical worst offender detection. So this one actually also inside the Speos. So inside the Speos, we already set all the buffer for each lenses. So this one will detect the dominant mechanical contribution for the SLA, the Straylight analysis. So in this article, we start from the buffer tree to identify the stronger noise contributor. Okay, so after we run few iteration, the buffer will be changing from the number 3 maybe to others number. Okay, so the workflow here will be running the simulation, and then the system will keep ranking the contributor and apply the absorbing coating to reduce the noise on the surface. Okay, so here is the next step. After they do the iteration, they will keep replacing the absorbing coating. So like just now I mentioned, the coating we can using the editor to edit the data, and also we can using the existing material if you have the material file. Otherwise, you can using the measurement data. So our company will having this kind of a measurement for BSDF scattering material. So you can send your sample to us, and then we can do the measurement to create this kind of coating profile. So you can use this profile for your this Speos simulation. So the impact for this kind of absorbing coating, that will reduce the scattering, reduce the detector noise, and improve the system SNR. So the iterative part will be the optimization loops. So as you can see here, we have a red box circle. So this thing is the iterative loop. So the loop actually is doing detect the offender, which is just now the buffer, and then they will apply the coating. So after apply the coating, it will recalculate the SNR. So keep repeating on this one until the SNR, until the target value. So this one, the major benefit for this automation, it will reduce the manual intervention on the workflow. So here is the final report and also the result. So as you can see, when initial the iteration, here we only have 4 iteration. So the optic signal and the noise initial. So we calculate the SNR. So here is the SNR for the system. So as you can see, when we changing the buffer, so you can see the coating that change, and then you can see the system signal and also the system noise. So when we changing on this one, and also the coating on the surface, you can see the system signal is keep increasing and the noise is keep reducing. So at the system SNR, you will see the final is like increasing. So that means improve the SMR will reduce the stray light on the surface. So here is the key advantage of the automated SLA workflow. So the first one is the root cause identification and reduce the engineering time, and all the coding replacement and optimization will be automated. And inside this simulation, you will including all the optical and mechanical. We call it optomechanical integration. Is an entire is a system-based analysis, and also the higher system robustness. So for the business overview, is a faster development cycle, and also reduce the prototype cost, and you have a better imaging performance using this workflow. So for the conclusion here, so the key takeaway, Straylight is the system level challenge. So the optical, mechanical analysis must work together. Is an optomechanical workflow. So the automation greatly accelerate this kind of optimization, and the Ansys Optics enable this scalable SLA workflow, which we combine the software, for example, the Ansys Zemax OpticStudio and also the Ansys Speos. And for the final, this automated Straylight analysis enable the faster development of the high performance optical system.